Dacă e ok și în online.
Le-am și trimis? E partea mea și
ok. Trebuie să mă prezint, nu? Da. Salutări tuturor, eu sunt Andy. Sunt student la doctorat în anul 2 la... Ce? În engleză. Oh, ok. Hi everyone, my name is Andy. I'm a PhD student in the second year at University of Bucharest. I'm also working at CrowdStrike on malware analysis and LLMs and stuff like that. Today we're going to hold a workshop called Fine-Tuning Transformers for Nitro NLP for the goal of preparing you for the hackathon tomorrow, right? Yeah, okay. We're going to go through a bit of theory, presenting what is an embedding, what is one-hot encoding, word2vec, and then we're going to follow up with transformers, and then we're going to fine-tune our transformer for one or two specific tasks. All right. Okay. The goal of this notebook is to teach you how to fine-tune. Okay. How to fine-tune the pre-trained transformer for a real NLP tasks in enough time and in an efficient way to apply it to the hackathon. We will fine-tune a transformer called Roberta on emotion classification and fake news detection tasks. And by the end of this notebook, you'll be able to do the exact same thing I did with the same recipe for any classification task and any data set that you like. A small disclaimer or a note, material is based on the tutorial offered by Dana 2 years ago, which served as inspiration structure for this notebook. All right, and as resources, as you can see in the Discord as well, I have the data sets for emotional analysis and fake news detection, and as model we'll use Roberta base. You can use whatever you want, BERT, dBERT, Roberta, whatever. All right. So why do transformers work? How did we get to transformers? The main problem and the main question that we need to ask is how do we convert a text, or rather a string, into something that a computer can parse and can understand, which is, by all of you know, numbers. We're going to answer this question in 3 stages. First of all, we're going to go through everything that happened before transformers, and then what are transformers, what changed, what problem they solved, and then after transformers, what was new, and what are the next steps for LLMs as well. We're going to start with embeddings. An embedding is basically a way of converting, as I said, categorical data, words, IDs, or tokens into vectors of numbers, or other numbers. The first attempt of embedding is called one-hot encoding. So imagine you have a vocabulary, maybe, I don't know, 1,000, 2,000, 50,000 words. Each word can become a vector of 50,000 numbers, and all of them would be zeros except a single one at the word's position. So for the vocabulary called cat, dog, bank, and river, we would have ones on the first diagonal, and 0 otherwise. This is what we call a sparse matrix, because sparse meaning it has a lot of zeros. It's mostly zeros and a few ones. The problem with this type of encoding is that it has a lot of dimensions per word, like the whole vocabulary size, which is enormous, and as I said, mostly empty. Every word is equally distant from every other word, so the distance, the vectorial distance between cat and dog would be square root of 2. Between cat and bank would be also square root of 2, which doesn't really capture any semantic or contextual meaning. And as I said, it has 0 semantic information encoded. You would maybe ask, why would someone use one-hot encoding if it's marketed in a way that isn't really useful? Well, first of all, it's very simple. It was the first thing that people thought about. It was trivial. We didn't need training for it. It was easy to use, to implement. It was mostly a historical start for the whole encoding and embedding stuff, and it works rather okay for very small vocabularies. So maybe for like 100 words, it works in a very specific context. The second attempt that people had at embeddings was called word2vec, or rather not the second, but one of the most relevant attempts was called word2vec, which we call dense embeddings. Word2vec aims to combat the loss of the meaning by representing represented by the one hot encoder, and it's trained on billions of sentences on wikis and a lot of data. As an input, it has a word, and the output is basically predictions for its neighbors. So, for example, for cat, you will have a 300 dimension vector like this, and every single number in that vector would be something that the word is related to. It captures the whole context. So, for example, if we take the vector for king, for example, you will have like 300 dimensions numbers in the king vector, and we subtract the vector for man, and we add the vector for a woman, we would get something similar, or rather the exact same vector for queen, which was pretty interesting at the time, because the model, the neural network, did not receive anything, any sentence like, a man plus a woman, a man plus a crown is a king, or a woman that is not a man and is a royalty is a queen, or such things like that. So it basically learned only by the numbers. The geometry of the vector encoded the meaning. Word2Vec has a few problems. One of them being the problem of polysemy. So the same vector is applied to the same word disregarding its meaning of in a sentence. So if I say I sat on the bank of the river, meaning I sat near the river, and I deposited money at the bank would have the exact same vector encoding in the same sentences, in each sentence, even though it has a different meaning. So it does not capture any type of meaning. It's a one fixed vector forever, regardless of context. The other problem that Word2Vec has is the problem of representing the sentences. So for the sentence cat eats mouse, and mouse eats cat, if you would like to somehow encode that sentence, and how would you do an encoding of a sentence, the first thing that comes to mind is averaging all the vector inputs of each word. And if you compute the average of each vector of each word in the sentence, we would get an identical vector. So the word order is completely lost, and we don't capture the meaning of the words in relationship to the context. Maybe some possible questions would be there if you ask. It would be why output 300? 300 was a good trade-off between performance and cost at that time when training. And to answer the same question as we did to the one-hot encoding, is it still used? Yes, it's sometimes still used in recommender systems, maybe some lightweight search stuff, but not. We're slowly drifting away from Word2Vec. All right, and this gets us to the main point of today's lecture, which is transformers. So everything that we saw until now guided us to reach transformers. So to sum up a bit, one-hot encoding had no meaning, Word2Vec had meaning but had no context, and then transformers kind of solves the context problem. So in transformers, each word could look at all the other words in a sentence and decide which ones are relevant to its meaning. So for example, if I say I deposited money at the bank, the same sentence from before, the relationship between bank and deposited and money would be stronger than the relationship between bank and I, or bank and at, or the. So the vector would encode something related to a financial institution. The same in I sat on the bank of the river. Bank would be more strongly correlated with river and sat. All right, what changed with transformers, so what made transformers actually useful, was something called the attention, or rather self-attention, which is a mechanism that tells us what words are relevant to understand the word that we are trying to encode, and they assign some informative weights. So as a quick overview of how would the transformer work, the first step would be tokenizing and embedding, which all of them kind of do. So tokenizing the text into tokens and then embedding in a table of embeddings that is very similar to Word2Vec. Until now, it's like nothing new. The second step would be to add some positional embeddings. So to those initial table embeddings, we're adding, we're telling the model what position in the sentence each word has in order to kind of learn that as well in the process of training for each token. The third step, which is the main value of a transformer, would be the self-attention. So in the self-attention, it's something a bit more complicated than this. I think last year I held a lecture on it, if you want to watch it on YouTube, where I went into detail. But self-attention is basically every token looks at other tokens, and they assign weights. This is done, for example, in BERT, which we're going to use 12 times in 12 layers. So each layer captures representation of those words in the sentence. The earlier layers capture the grammar, the syntax, so more high-level stuff, and the later layers capture the sense, the semantic relationship, the context of the words in the sentence. And the last step of the transformer would be the output, which is a vector contextualized for each token. So for each word, but for a different sentence, we would have a different vector, which was the initial wish that we had that wasn't fulfilled by word to vector. So now transformers came around in 2017 with the purpose of translation. That was the initial purpose the transformers were created for. And their architecture is composed of an encoder and a decoder, so both things. The encoder is a component that reads the input, constructs the representation of the vocabulary, or rather the source of the input, and the decoder is a generator, basically, which generates the desired language word by word and look at the output of the encoder. So they are like two components which work together. One understands, one generates. But not all transformers are the same. For our purposes, the difference between an encoder and the decoder is there are transformers which are encoder only, and transformers and what we call modern LLMs which are decoder only. The transformers which are encoder only is what we're going to work with today. For example, BERT, Roberta, DBERT, whatever. They see the whole sentence at once. They are good at understanding and the relationship of the words in the text, and they are mainly used for classification, similarity, name entity recognition, and the decoder only, which is GPT or Llama, for example, they only look at the past tokens left to right, and they try to predict the next tokens. This is why they are good at generating text. So they are mainly used for code generation, summarization, or chatbots, virtual chats, whatever. And as I said, GPT-4, Llama, Mistral, and so on. Today we're going to use an encoder to classify text, not generate it. And the last things I want to talk about regarding the actual theory stuff is the CLS token. The family of transformers we're going to use, called BERT, uses a special CLS token to every input. So basically, if I have the sentence, this movie was terrible, where what BERT is going to see is CLS, this movie was terrible, SEP. SEP is a separator. But CLS is basically a blank token. It has no meaning. It is appended to every sentence that we're feeding it. It is placed only at the start of every input, and its job is to collect information from every other token in that sentence in order to represent it at the end of the actual understanding, to feed into the classifier. So we're not going to look at the outputs of each token in the sentence. We're going to look at the vector that is outputted by CLS, and using that, we're going to do the classification, because we're going to feed it into a linear layer of a network and then get our prediction. And this is what we call a classification head. So to sum it up, the universal fine-tuning recipe of a transformer, or rather of this transformer, is basically we have a pre-trained encoder, in this case BERT or Roberta, and then we have the CLS embedding with 768 dimensions, which is a summary of the whole input. Then we append the linear layer, or rather the task head, which is randomly initialized, and we learn that during the fine-tuning. And then we predict. That's about it. Sounds simple, right? All right. So one more observation regarding this. you would maybe ask, if we have such powerful LLMs today, like GPT, Gemini, Claude, Llama, whatever, why do we bother fine-tuning a transformer when we can just prompt an LLM, right? Well, because of the task-specific, the specific task that we have. So you can describe the task in a prompt to the LLM, and you're gonna get an answer. If we're gonna say, classify this emotion in the text as one, sadness, joy, whatever, and the text would be, I just got promoted, GPT-4 is gonna answer joy. Or at some point it's gonna answer joy. It's not necessarily something he's gonna answer every time. But looking at the actual costs and at a table with a comparison between GPT and a fine-tuned transformer, GPT per 1 million predictions costs like $100. And Roberta costs like $1 if it's self-hosted. And has a much lower latency per prediction compared to GPT, which is you would call through an API or whatever, and it has a much higher latency. GPT-4 is not deterministic, so it's not, it doesn't really give us the same output every time. It could hallucinate a bit. It could say, I think the emotion is joy. Maybe if you prompt it 100 times, it will say something different. And it varies with prompt wording. If you change the prompt a bit, the results may vary. So it's not deterministic at all. Works offline, no. It may work offline if we have a local LLM, but again, it's quite heavy. And modern LLMs are a good baseline, but usually a fine-tuned transformer on our specific task is much lightweight, and it usually has a higher accuracy or F1 score or whatever your metric is. So the core trade-off would be, yeah, we can use prompts when you have no labeled data, when we need something very quick or a result, or the task requires some kind of word knowledge, not necessarily only understanding of pattern recognition. But fine-tuning wins when we have labeled data, even 100 examples would help, when we need a structured output and when latency matters. When we want fast answers and APIs are slow, and our task is well-defined and pretty niche, we can do fine-tuning of an transformer. And you would say, yeah, why not just fine-tune an LLM then? Well, you can, which is what we call instruction tuning, or you can fine-tune a smaller LLM with LoRa or PEFT. And it's what makes huge LLMs like GPT, Gemini, or Llama work. But fine-tuning a Roberta could be done in this collab. And fine-tuning a Llama would take hours to maybe days. It would require more powerful GPUs, and the complexity of that would be significantly higher than the complexity of this notebook. And the accuracy you would get isn't necessarily worth the cost that you're gonna have in addition to fine-tuning a transformer. So for classification tests specifically on easier or rather simpler data, a fine-tuned 100 million encoder would match or even beat a prompted, I don't know, 10 billion LLM sometimes. Because bigger is not always better when the task is narrow and you have labeled data. All right, let's get to the workshop as a step-by-step example. For today, I prepared two tasks. Task 1 would be emotion classification, and task 2 would be fake news detection. The model would be Roberta base, and we're going to use Hugging Face transformers plus a trainer API. Before you run any of the code, make sure you're on a GPU, not a CPU. You would go there, you would go change runtime type and choose a GPU. Otherwise, you're going to hate your life when running this. We would use the libraries transformers, dataset, evaluate, and accelerate. In order to check if you actually have access to a GPU, you can run !NVIDIA SMI to see the actual information about the GPU you're using. All right, here I can see that I'm using a Tesla T4, nothing really crazy about it. I can see the usage of it, so this kind of stuff. The first thing that we're gonna do, again, this is only a sanity check. We can check if a GPU is available with torch.cuda.is_available. And we can also see its name. It's the same that you can do with NVIDIA SMI. All right, so for the task, we're gonna define some variables. I defined also a variable called task because as I presented before, we can use both of them and the code would change like 4 lines. It's very reproducible. So the first task would be emotion, and the second task would be fake news, which I commented. You'll see why later. The model name is Roberta Base, which you can see on the Hugging Face as well with the same name. The data set name is again on the Hugging Face as well. If I go to there, I think, wait, you can see how I found it. So this is where you get the actual names of the models, but you'll have a cell about that later. All right. And the dataset name was their AI emotion. I basically sorted by downloads and picked one that had emotion in the name. We're going to also define the number of labels because that is very important. Because the emotion, if you do some data analysis or rather you look through the data on Hugging Face, you would say that it has 6 emotions like anger, joy, sadness, or so on. And the metric name that we're trying to optimize or rather look at when we're training is F1. Does anyone know what F1 is? Or why would we use F1? No worries. I'll get to that later. I just wanted to see if someone would spoil it because I have a cell about that anyway. Yeah?
Because we could have an unbalanced set.
Mm-hmm. Yeah, exactly. Yeah, that's correct. So basically, if I have no way of knowing, I mean, I have some ways of knowing if my set is balanced, but I was too lazy to, I don't know, make a split of it which is balanced, or rather, I don't know if it can be balanced at like 2,000 samples. So I could have like 80% of it being joy and the rest of 20% being split between the 5 possible emotions. This means it's not balanced. So the accuracy would be high if it learns to predict the single emotion that dominates the data set, but the actual performance would not be that good because the other 5 metrics have, the other 5 emotions have to suffer. So the F1 metric is basically an aggregation between precision and recall, which is weighted of each of the emotions that I'm trying to predict. So it takes into account all the predictions, which is to combat the unbalanced data set. All right, the training hyperparameters would be max sequence length. So the max token length is, I put it at 128, which is enough for short text and sentences such as the ones that we have in the data. You could up that like, I don't know, 512, depending on the task. Maybe you have bigger samples of fake news and anything. The batch size is 16, basically how many samples per training step we're gonna take into a batch. If you up that, you may have like, performance issues with Colab if it's too much, depending on the data. If you have performance issues, you can do 8 or even 4. The number of epochs is basically how many times we are going through the training data to train our transformers. And the learning rate is pretty standard, is 2e minus 5, is basically how fast the model updates its weights. This is a standard learning rate for BERT transformers. Okay, now we have the model, we have the data set. What do we do with it? So first of all, we need to actually process our data set because the data set basically are, I don't know, 2,000, 10,000, 20,000 samples, and now we need to do something with it. In order to train, we need to split it into three categories. We need to do training, validation, and testing. What's the difference between each of them? This comes pre-training and pre-split, and most of the time in a hackathon where you will do that, you need to split it yourself because the data won't be split for you on Hugging Face or any notebook you'll find. A good rule of thumb would be the training should be like, I don't know, 70%, the validation 15%, and the test 15%, depending on the data set size. For example, in my data set, I have something like 70, 15, 15. Depending on the data set size, you could have like 80, 10, 10. You can just test around with this. But this is a good rule of thumb. The training is basically which data the model learns from. So it's most of the samples that you're feeding in order for the model to learn. The validation is what we check after each epoch, which is what gives us the loss and used to tune the hyperparameters and even catch overfitting. So the model never trains on the validation data. And the test is what we touch at the very end to see our real performance or an unbiased result. As a warning, you would never tune your model based on the test set performance. If you do, it's no longer a real test because it's contaminated. All right, so knowing this, we're going to load the dataset. The dataset can be loaded pretty easily if we actually find it in the Hugging Face hub. You will just do load underscore dataset of the dataset name, which is the parameter that we declared before. And it's already pretty split into train, validation, and test. But you can do that yourself as well. So if the dataset isn't on Hugging Face hub, you can just define it yourself with load dataset CSV. Data files, you would split it into train, test, and validation or whatever. All right. The dataset that I chose had around 16,000 samples, and I chose only a fraction of it for the purpose of being faster with the notebook. So I split it into 2,000 for train, 500 for validation, and 500 for test. All right. Okay. Good. So an example from the training set would be, as I said, small sentences such as "I didn't feel humiliated" with the label 0. We don't know what the label 0 is yet, but we need to define the label mappings as well. Why? Because the transformer does not know what the label actually is, and we're putting a classification head on top of it. We need to define the label mappings in one sense and in the reverse. So the model needs to know what the integer is. You can take this info from the dataset card on the Hugging Face, or rather your own custom dataset. We know that 0 is sadness, 1 is joy, 2 is love, 3 is anger, 4 is fear, 5 is surprise. And for the fake news, 0 is fake and 1 is real. We also need to do the reverse mapping as well to actually fit those parameters when we're gonna train the classification head. So this is basically a pre-processing result. We can also see the first training example. So as I said, pretty small sentences, 128 characters would be fit for that. Okay, after we do the training, split, data validation, and the ID to label encoding, we're gonna load the tokenizer, which you heard about when I talked about transformers. The tokenizer is basically the component which converts the text into IDs, or rather numbers that that the model understands. The tokenizer must match the pre-trained model. You cannot mix one. I mean, you cannot use a BERT tokenizer for llama training or whatever you want to do. It's the same logic from before. Because the model is found on Hugging Face, you can also take the tokenizer with auto tokenizer from Hugging Face. It's really easy. And we can actually check, so this is everything you need to do. Everything else is optional because I want to show you what it looks like. The tokenizer, we can see what it actually does to a sentence. We can take an example text, we can .tokenize the example text, and then encode into IDs. So the original text was "this movie was absolutely terrible," and the tokens were this, G movie, G was, G absolutely, G terrible, and a dot. And the token IDs were those. Those are learned by the tokenizer when trained. You don't need to worry about those. This is just what the computer sees in order to be able to statistically do something regarding the context. And you can see the vocabulary size is 50K. You would ask, what is this G? This G is basically the byte representation for the tokenizer of Roberta. Because Roberta uses byte pair encoding, tokenization, which operates at byte level, instead of splitting into spaces and then tokenizing. It encodes the space as part of the following token. BERT, on the other hand, if we had used a simple BERT, uses word piece, not BPE. What does word piece do? Word piece does basically, instead of the G, it does 2 hashtags, which mean continuous previous token. And this G with a dot on it means space before token. And there's a comparison between all those encoders. So one hot word2vec BERT, which uses word piece, and Roberta, which uses BPE. The first ones, before transformers took the whole word, BERT and Roberta use subwords, but Roberta uses subwords on a byte level. What does that mean? This means that if we use only English words, it would not really make a difference. But with Roberta, we can actually use emojis and stuff like that because they're bytes and they can be represented in some kind of way. This is really the only difference. And the vocabulary size is a bit bigger than BERT's vocabulary size. Yeah, that would be it. They're both context aware. They both capture semantic information. One thing that BPE does not do, so what we're using right now, because BPE is still just a lookup table at this point, and after each tokenization, each token ID maps to a dimensional vector in an embedding similar to Word2Vec, as I said in the transformer step-by-step. The contextualization happens after this in the self-attentions layers of Roberta. So the context is added after the embedding lookup in the actual attentions layer. So this tokenizer has no intelligence whatsoever. It is only a dictionary, it is only a representation, it has, but the embedding matrix has word-level intelligence. All right. After we declare the tokenizer, we need to run our dataset through this tokenizer. So we're going to declare a preprocessing function, which is going to return tokenizer of our examples with truncation true. What does truncation mean? It means that if we have something bigger than 128 characters, which we declared before, it's gonna cut it, but hopefully not. The max length, which we already defined as 128, and padding is false. We're gonna talk about padding in the next cell. We're gonna apply these functions to the whole data set. So basically, we're gonna tokenize it, nothing too crazy. We're tokenizing the train data set, the validation, and the test one. And then, because I put padding false, does anyone know what padding would do here, or any intuition about what padding would be in this scenario? And why I put it as false? Because it's not really intuitive why I would put it as false. Okay, so basically because the max length we have is max sequence length, is 128 characters. As you saw, our inputs can be 20 characters, 50 characters, even max length characters. In order to parse those inputs into the classification head, or rather the neural network that we're going to train, they need to be the same size. If they need to be the same size, we need to make them the same size. So padding, if I put padding true, the 20 character sentence is going to have paddings like empty tokens to 128 characters, which is fine, but there is a more efficient way to do this. It's called a data collator, and it's a method that handles the padding. But it doesn't handle the padding per data set, it handles the padding per batch. So basically, if my batch is 16 sentences, if all of them are like small sentences, I don't know, 20, 30, 40, 20, 30 characters, it's gonna pad all of them to the biggest length in the batch, not 128. So we're not gonna have like a lot of empty and unnecessary tokens to 128 if the larger sentence in the batch is not 128 characters. It's a bit more efficient. All right. And you would declare it with data collator with padding of tokenizer equals tokenizer. That's about it. Then we need to define our evaluation metrics, so what we're gonna actually evaluate after we train and when we train. I used both F1 and accuracy to see the difference between them. As your colleague said, F1 would handle class imbalance, which is better than accuracy, and accuracy is an intuitive metric, the first that we think about. So we have a compute metric. We have some logits and labels, which are returned which are equal to the evaluation predictions. We will need to convert those logits, or rather, which will give us the probabilities, to the predicted class, and the logit with the highest values index we're gonna take and convert. And the F1 metric would be computed on an average weighted, because we want to account for class imbalance as well. And the accuracy is the accuracy. All right. Then we're gonna load our model. I know it's a lot of pre-processing or prerequisite stuff, but that's how it is. Then we're gonna load our model. We're gonna load it using AutoModel for sequence classification. What does that mean? That means we're automatically adding a classification head or the linear layer that I talked about on top of the transformer that we're using. The head is a CLS vector of 768 dimensions, followed by a linear layer, which we're adding, and then the number of labels as outputs, which is 6 in this case. So we're gonna declare the model as AutoModel for sequence classification from pre-trained of the model name, which is Roberta base, the number of labels which we need to do that in order to know how many outputs possible outputs we're having, which we're declaring here, and then the actual mappings from ID to label and from label to ID that we declared before in order to see, to actually tell him what to learn, because he needs to know the transformer, the linear layer needs to know the correct outputs for certain sentences. You don't need to necessarily count the parameters. I put that only to see how many would be. You can see that Roberta, our transformer, has 124 million parameters. That's about it. You can ignore the unexpected and missing stuff because when loading from for a different task or architecture, you would get some warnings or stuff like that, but you can ignore them. Okay, and you can see the architecture that I talked about in the previous cell. We have a dense layer, a dropout, and an out linear layer. All right, and now we need to actually configure our trainer. The training arguments would be the output director. You can see those in the Hugging Face documentation as well. But what we're using is an output directory because we need to save our best checkpoint or a checkpoint at that point. The base hyperparameters would be how many epochs are we training for, which we declared at the beginning is 3. The learning rate, which is we declared as this. The batch size and the eval batch size, which in this case we're doing the same. And the await decay for the L2 regularization in order to regularize the training as well. How we're going to evaluate and save? We're going to evaluate by epoch. So after we go through the 2,000 samples that we're having in the train, it does an evaluation and it gives us back a loss and an F1 or whatever. And at the end of the training, we're going to load the best model, or rather the best checkpoint. And we're going to log that as well every 50 steps. And for reproducibility's sake of this notebook, I put it a 42 seed as well to initialize the way it's the same if you run it again. All right, these are the parameters that we had. And then after we create the training argument, so this is basically these are all the training arguments. We need to create the trainer object within the Hugging Face framework. So this wraps the entire thing that we did until now, the training loop, like the forward pass, the loss, the backpropagation, the eval, the save, the everything. So the trainer would be trainer of the model. The arguments would be the training as from before. The train dataset is the tokenized dataset we did at the beginning. The eval dataset is the tokenized dataset of the validation. Attention, not test, but validation. The test is something that we're going to use later only for our sake to see what the performance is. The processing class is the tokenizer. The data collator is the data collator that we declared before. And the compute matrix function is the compute matrix that we declared as well at the beginning. So this is basically the trainer. In order to train the model, you just do train equals trainer.train. That's the most efficient way as far as I know. This would run for around 3 to 5 minutes, depending on how Colab decides to collaborate. But what this call would do is it would take the forward pass, so the model prediction. It would compute also the cross entropy for classification. It would do the backpropagation. It would update the weights using ADAMW optimizer. It would evaluate after each epoch, and it would save the best checkpoint, which would probably be the last, considering we're training for 3 epochs. After we train, we can see that at the first epoch we had this loss, and F1 score of 0.59 and an accuracy of 68%. After the second epoch, it jumped up to 0.79 and 0.8, and after the third epoch, it jumped to 0.84 and 0.85. So in theory, we could train for, I don't know, maybe 5 to 10 epochs to see where it starts to overfit and that on, but for demonstration purposes, we're training for 3 epochs, and we're seeing that the accuracy, both the accuracy and the F1 improves. And probably the model is pretty balanced, considering the F1 score is similar to the accuracy. All right. We can evaluate on the test set as well, because again, this tells us that the model is doing fine, but we don't know what it does on unseen data. So we can evaluate on the test set as well. We can take the test results with the method .evaluate of the tokenized data set of test. And for each item in test underscore results, we can print it. And the performance on the test would be the F1 is slightly lower than the F1 of the validation test, and the accuracy is slightly lower as well. So again, on unseen data, you would expect it to have a slightly lower performance, but you can see that it works as well. So it's better than the baseline. Okay, now you ask, how would you run on new examples? Okay, you split your data, but you want to run on new examples. You have 2 ways of doing that. Doing through the pipeline method, which is a simple one-liner, which I would use personally, or doing it manual. So basically, you tokenize it yourself, you load in the model, and you perform the argmax function as well in order to take the probabilities for your classification result. I'll present you both methods. So if you would use the pipeline, this has several parameters that you can choose from. One of them is text classification. You can also have named recognition or semantic similarity or only similarity. This basically tells us what task are we actually trying, did we fine tune for. And you need to define the task, which you have a predefined list on Hugging Face. You need to define the model, the tokenizer, and the device which I wanted to make sure is the GPU. So this is the classifier. Then you take your text examples. So if your task is emotion, I put in some placeholders there, like I just got promoted at work, I'm so happy, my dog passed away yesterday, I miss him so much. These are basically the strings that I want to predict on. And for each text in text, the result would be classifier of text of 0. And that would be the label. And you can see the predictions that our model has. So for the first one, it has actually a confidence as well, which is the logit probability of 0.966 of joy. We can see that it's not really confident, and it actually is pretty, it's not that good on the fourth sentence. So the presentation is tomorrow, and I haven't prepared, This doesn't sound like joy to me. And its confidence is low, and it kind of misrepresents that. So on newer samples, what you can see is that on even newer samples, unseen ones that are not in the same format as the ones that it was trained on, it can actually predict wrong. So the more data you have and the more generalized it is, the better the performance would be. But these are written by me, so they're not similar to the training data. If you would like to do manual inference for some reason and you don't like doing only this, you would need to do a lot of stuff. So first of all, you will need to set the model to evaluation mode with model.eval to disable the dropout layers that we use during training or regularization. You would need to tokenize your input. You can just feed it like I did before. I didn't feed it directly because it went to the pipeline of classifier, which I declared the tokenizer, but you need to tokenize the input as well. Truncate it again with the max late, and because I was too lazy to do the data collator, I put a padding through. then you would need to move the inputs to the, I actually had a bug and I was not sure why to do this, but you need to move the inputs to the same device as the model because you would otherwise get an error. And then run a forward pass without computing the gradients with torch.nograd because it saves memory and it would speed up the inference. The outputs that you're gonna get are some logits. You can access them by outputs.logits. And then you would need to convert those to probabilities using softmax. So torch.softmax of those logits. And if you have those logits, you can actually get the predicted class. And this is how you would do it manually. So you would take the logits, the index of the logit with the highest probability, and find that with your mapping of ID to label, and you would also get the confidence of the probabilities with the .item method. All right. This is Natasha. Okay. As a bonus, when you would, after you have your model, for example, so you got your F1 score, you got your accuracy, you're happy with that. Maybe you want to see what the model is getting wrong or where you can actually improve. I'm a data scientist for work, and finding improvement gaps is kind of my job. So what you would do in this case for this type of problem would be to build a confusion matrix and analyze the errors. So in order to do that, you will need to take all of your predictions and outputs and labels and create your confusion matrix, which we can use by we can do by either sklearn or Seaborn or whatever library you want to use. The confusion matrix takes the true labels and the predicted labels, and you can take those as we did before by predictions.output of those label IDs that we predict, and the label names would be from the mapping that we did from ID to label and vice versa. We can plot the confusion matrix using Seaborn. So basically it's a heat map of the confusion matrix that we're creating in a blue tone, and on the X line we're gonna have the label names, and on the Y we're gonna also have the label names. So how this looks is something like this. What the confusion matrix is basically an aggregation of all our outputs and where it went wrong. So for example, a good confusion matrix would have the first diagonal would be like very colorful, because we want to, when the true label is sadness and the predicted label is sadness, we want this to be the maximum it could be. We can see that for love and joy, it kind of confuses them a bit. It confuses them for like multiple reasons. One of them being that there are not really so many samples with love and joy, with love. So for love, the true label would be around, I don't know, 30, 40 maximum of samples. So having such little samples, it does not necessarily learn to distinguish between love and joy. Another example would be surprise. Surprise has even fewer samples, and you can see that surprise and fear actually have the same number of predicted labels. So it's not really working on that. You can fix that by either oversampling your data set or taking more data for those specific emotions. But as you can see, your model had like, I don't know, 85% F1 score or 85 F1 score. It's good, but you can improve it on these types of areas. So a confusion matrix is something that you might want to do if you're aiming for the stars in the hackathon. I don't have much time, but what I want to do to tell you is that if you can switch tasks really easy for fake news detection. So if you go to one of the first cells, just to see, because the transformer fine-tuning is mostly the same. What you would change is actually only the data. If I comment this and uncomment this, it basically replaces everything that I had related to emotion classification, and it goes to fake news. The only thing that changes is the model, is the data set name, the number of labels, and the tasks. And the task is basically, I used only this parameter only to declare some more data to test on, nothing too wild. So you can test it out yourself even on your data if you want. Besides that, where was it? Yeah, no, that would be it. So if you would run all, you would get only results for the fake news detection or whatsoever. So to sum it up, what you would do for a hackathon, because I talked a lot and maybe it was not really clear in some areas. The step one would be to find the model that you want to actually use. You would go to huggingface.models and underline models. You would search for Bert or Roberta or dBert or something base or your specific domain. Maybe you need to do it for emotions. Maybe someone did it better for emotions. Maybe you're restricted to use the base model. Maybe you want to use a smaller model with a lot of data rather than a bigger model with fewer data. You would just pick one from here. You maybe sort it by downloads or by popularity, and you pick one from here. Then if you want to do, maybe if you do not have a data set, you would search your data set on /datasets or load your own with, as I shown you. You would fill in the config as well. So your model name, your dataset name, the number of labels, if it's 2 for a binary classification like fake news detection, maybe 10 for emotion detection. You would look at this notebook and then check the confusion matrix to find where it fails. These are some common models by language. So for English, basically you would use maybe Roberta base or Distilbert base uncased. For Romanian, as Dana mentioned 2 years ago, I put it in the resources as well. You have a centralized space dedicated to Romanian language models, specifically built using transformer architectures, and actually a consistent framework for evaluating those. They're very similar in name. I think it's called Robert, not Roberta. So do not confuse the English-based one with the Romanian transformer. But you can actually find transformers for Romanian tasks as well if you have Romanian data, not English one. Of course, you can also take a multilingual one called XLM Roberta base if you have multilingual tasks. And if you need even more resources, I linked in the notebook the transformers paper, so the paper that introduced those things that we talked about today. It's pretty heavy to go through, but you can also check how an encoder looks and how a decoder looks, how the whole architecture works, and maybe get something from it. I also included some website I found regarding the illustrated transformer. So these guys kind of will go through a high-level look and then go to some low-level stuff about transformers, encoders, and decoders. They have actual examples, and they explain what each layer is, what each layer does, how each embedding relates to the self-attention and all that stuff. So make sure to check out that as well if you want some more in-depth stuff. And then a small observation regarding the BERT family. I linked also the dBERTA as well. I did not use dBERTA because, so BERT is basically, it has a slightly lower performance than Roberta, which I use today, which has almost equal performance to dBERTA depending on the tasks and what I want to do with it. Okay. You can actually use whatever you want for fine-tuning, but my advice would be to start with Roberta because it's the basic for NLP tasks. But depending on your task, you might want to use, I don't know, maybe newer stuff. dBERTA, if I'm not mistaken, has a bit more parameters than Roberta. But you can also use the large models if you have the computation power. So BERT and Roberta have the exact same architecture of 125 million parameters. dBERTA, the basic one, has 140 million, and the V3, which is like the most recent tiny, the BERT has like 180 million. The difference is small and task dependent, but depending on your hackathon objective, it may help switching the model slightly. All right, I think that's the end of the notebook and my blabbering. Do you have any questions?
There was a lot of I know. Basically, we don't have any bad experience regarding AI, so this was like a lot.
Mm-hmm.
We will really watch if something like that, and we'll basically brush up on everything.
Yeah, I tried to not go into much detail about how transformers work because that's a whole another discussion. I have a video from last year about this. This was mostly like, I know you would not understand everything from it because it took a while for me to put it together as well, and I had to relearn some principles as well. But the goal was to mostly give you something that you would go through and remember the different, mainly what is a transformer, what is an encoder, what is a decoder, why would you use that instead of that, and to have some code base that would help you with it. And in my opinion, you could shorten the code up if you would like, because it's very educational, pedagogic, and so on. But I think it would help in the context of a hackathon. No worries. And if you have, my work field is actually kind of related to transformers, but I haven't fine-tuned one until today since my first year of master's, which was, I don't know, 3 or 4 years ago. But if you have any questions regarding, I don't know, LLM stuff, prompt optimizing, fine-tuning LLMs, you could ask if you want.
How hard can these transformers get you? As in, what's like a big task, complicated task, where this would basically outmatch big LLMs and basically save lots of money?
I actually wrote something about that. Let me see, because did I have some numbers? Yeah. Oh, okay, yeah. So I expected the question to be, because I talked about encoders and decoders, right? And I said that the original architecture would be encoder plus decoder used for translation. And what we use today is encoder only. So you're asking how far would that get us? Only encoder, only decoder. So an encoder-decoder model would not necessarily be better than a decoder only, for example, like modern LLMs, because it's very task dependent. So for classification, we're not trying to generate anything. So for this type of task, we're not generating anything. And we would have a lot of parameters, unused parameters in our model that would give us more latency, more cost, more whatever. It's basically like if you would try to use an encoder-decoder for a encoder-only task, it's basically going with a truck to Lidl to make your to do your groceries. You can go with your car or your truck, but the result is the same because you're buying the same quantity, and it works the same. So what is the reality today is that scale kind of beats architecture lately in this context. So a very large decoder only, such as GPT, can beat a small decoder only at its own tasks, like translation. In 2017, when transformers were released, the encoder plus decoder was used for translation. It was like, okay, wow, that's nice. In 2018, BERT was launched, and it was encoder only, which means it was for the sole purpose of text understanding. And people were okay with that. Then 1 year later, T5 was released. T5 was a bigger model, is a bigger model, which is encoder plus decoder, which was even better at doing translation and understanding text. So people kind of went back to that for a bit. But in 2020, GPT-3 was released and the apocalypse went down on us because GPT-3 was trained only as a decoder-only model on lots of data, so billions, trillions of data, whatever. And it was good at anything. It started being good at anything. And nowadays we have GPT-4o and GPT-5 point whatever is now, which are, again, decoder-only. And they scaled so much that they dominate every kind of task. So researchers kind of figured out that they don't need both components, and they just need to scale a lot. To honestly answer your question, I have no idea how much they could possibly scale up to anymore, but decoder-only models seem to dominate the market right now.
Thanks.
You're welcome. Yeah, and as a comparison, what we use currently had 125 million parameters. GPT-3 had 175 billion, and GPT-4 has around 2 trillion, I think, 1.8 trillion. I have no idea how many GPT-5 has. I have no idea where they keep finding more data. I think they reuse it at this point. It's contaminated, but yeah.